Welcome to the next video in this series. So in the previous video we discussed the concept of we discussed the classification based on the symmetry of the signals, where we defined even and odd signals. We did some mathematical analysis. We then derived mathematically how we can derive an odd and even components. I also gave you a physical relevance that when you substitute t by minus t, physically it means you are folding your signal. Then your original signal and folder signal, together they combine through addition or subtraction to give you the even and odd components. But if you remember in our first video, we had said that the amplitude, the value of a signal, it may be the real valued, sometimes it may be complex valued. Now the concept of symmetry that we have defined here, it was in terms of a real value signal. That is to say, I have a signal x of t, it has a real valued amplitude. Right? But what if my signals are complex valued? Fine. So we do have a concept of symmetry for complex valued signals. So let me just write it down here so that you can put it in your notes. If we have a complex valued signal, complex valued means the amplitude is of the form a plus iota b, where iota is the complex, the under root of -1 is a complex quantity. So a complex valued signal, so I am assuming that my signal x of t, it's not a real valued signal, it is a complex valued signal. So we don't have the normal concept of symmetry here, but we have a concept of what's known as the conjugate symmetry. Those who have done a course on complex algebra, maybe आपने किया होगा in your 12th standard, या even your first second semester engineering, you may be aware of the complex numbers. There's the concept of conjugate symmetry. Right? And a complex valued signal, it is said to have conjugate symmetry if it satisfies this relation that x of minus t is x conjugate we normally show using an asterisk sign in the superscript, right? And this x conjugate t, it is basically the complex conjugate of x of t. So let me put things in a better perspective. Say suppose I have a signal which is complex valued x of t, which means I can always express it in this form: a real part and an imaginary part. Fine. That's how we represent one of the representations of complex numbers. This is the real part and this is the complex part. Then we define the complex conjugate as this: a of t minus jbt. Okay. Now from the condition here that if a complex valued signal is having a conjugate symmetry, then by that logic x of minus t is equivalent to x of conjugate t. Okay. Which means x of t, just put minus t here, it will be a of minus t plus j of b minus t will be equivalent to a of t minus jbt. Right? And if you compare real and imaginary parts, after comparing the two sides, the left hand side and the right hand side, you will have a of minus t is equivalent to a of t, and b of minus t is equivalent to minus b of t. If this is true, then this follows. Which means if we are assuming that a complex valued signal has conjugate symmetry, then its real part is even, because this is the definition of even signal. If you go back to the second video, this is the definition of an even signal. And this is the definition of an odd signal. Fine. So a small generalization here, that a complex valued signal x of t is conjugate symmetric if its real part is even and its imaginary part is odd. Fine. So we have defined symmetry that applies to real value signals. Then we have defined conjugate symmetry that applies to complex value signal. And in a way, we have established a relationship between conjugate symmetry and the real valued symmetry in terms of these even and odd components. Fine. So that was the classification based on the symmetry. Then we have a third basis for classification. We defined in terms of independent variable time. We classified on the basis of symmetry. Now third classification is based on the property of periodicity. This is something you must have heard about, and on this basis you can either have a periodic signal or you may have an aperiodic and non-periodic signal. Definitions are self-explanatory. A periodic signal, it repeats itself. To be precise, it repeats itself after some time interval. So if I use the mathematical definition of my signal, so if I have a periodic signal x of t, it actually is a function that satisfies this condition, that's x of t is equivalent to x of t plus some time interval, capital T, after which it repeats. Again, this is true for all the time values t. Okay? And the capital T here is a positive constant. It is a positive constant. And we say this t basically is the time period. Fine. So this signal will repeat itself after time, capital T. We have many examples. We have sinusoidal waves, cosine wave, which is included in the sinusoidal wave. These are periodic signals. They repeat after a specific time interval. Fine. And if I just do a bit of in-depth analysis, although again we will be discussing it separately. Suppose I have a signal like this. Fine. Suppose this is 0, then we have t naught, after which it repeats, then 2t naught, 3t naught, and so on. Fine. And it can as well go with the negative axis like this. Say then this is minus t naught minus 2t naught. Fine. So I can say that the signal, this particular signal x of t, it repeats after t naught. Fine. So after every t naught amount of time passes away, the signal repeats itself. So I can put a general relation for this, that x of t is equivalent to x of t plus mt naught. Fine. Where m is an integer. Fine. Like I can have x of t plus t naught, which is true. I can again have x of t plus 2t naught, which is again true. I can then have x of t plus 3t naught, which is again true. So the signal repeats itself, t after t naught, after 2t naught, after 3t naught. And there is a typical value, there is a typical quantity that we associate with it, that will be the smallest value of this time period of this positive constant t that satisfies this periodicity equation, that is, say, this equation that satisfies equation 1 is called the fundamental period. Fine. And you know that frequency and time, they share a inverse relationship. So if your t is the fundamental period, we also define the fundamental frequency as f is equivalent to 1 by t. Okay? So it basically describes how frequently the periodic signal xt repeats itself. These are some quantities which I'm sure you must be familiar with. And sometimes we also define the angular frequency, which is defined as omega is equal to 2 pi f. Yeah, you can always express in terms of the fundamental period, that's 2 pi by t. So these are some few things associated with the periodic signal. It will have the time period, and if this time period is the smallest value that satisfies the relationship, we call it the fundamental period. Fine. Then the inverse of this fundamental period, it will be your fundamental frequency, and you can also express in terms of what you call the angular frequency. Fine. And in case this relation is not satisfied, I mean, you are not able to find any value of t for which your signal x of t repeats, we simply say it is a non-periodic signal. Right? And you can generalize the same thing for a discrete time case. So for a discrete time case, I have x of n. It will be equivalent to x of n plus capital N. Again, for all values of the small n. And n is a positive, it has to be an integer because we are talking about discrete time. It cannot be an decimal and all that. So it has, as for a fraction, it has to be an integer. And the smallest value, same thing here, smallest value of the integer n for which this equation is satisfied is called the fundamental period. Fine. और जो corresponding frequency होगा, normally discrete case में we show it like you, this omega, it will be 2 pi by n. This is again angular frequency, but in the discrete time domain. Fine. So this is the classification based on the periodicity. But there is a difference. We will be discussing that thing separately. The concept of periodicity as we apply in continuous time case is slightly different than what we apply in the discrete time case. We will be taking that separately. We will be doing some numerical problems on that. But for the time being, as far as classification is concerned, you may either have periodic signal, in which case the signal repeats, and the smallest time period after which the signal repeats is the fundamental time period. Then we have these are major classifications, like based on time, continuous and discrete time, a very major classification that we will be using a lot in this course. Then again, based on symmetry is a very important classification. Same thing goes in terms of periodicity, again a very important classification. Then we also sometimes classify based on the deterministic, based on the nature of the signal, on the basis of which we have either deterministic and a random signal. Fine. Now a deterministic signal is a signal for which you have a full developed mathematical representation. Yeah, I can put it like this way, that a deterministic signal is that signal which has no uncertainty. You know exactly how this signal is going to behave, which is only possible when we have a full-fledged mathematical definition. For example, if I have x of t is equivalent to sine of omega t. Now this is a signal which is mathematically, explicitly defined. It's just pure sine wave. And you give any value of t, you will be able to determine what is the value of this signal. For example, we are talking of time t is equal to 0. It will have a value of something. But you can also say with 100% certainty that at time t is equal to 10, what will be its value? Because it is pretty much defined by this mathematical expression. Now, contrast to this, we have random signals, which are uncertain. In the sense that you don't have a well-developed mathematical model for them. And when you don't have a mathematical expression for a particular signal, you can't predict what its value. You may predict with certain probability, but you won't be able to predict the exact nature how this signal will behave. So we call that a random signal. And there is a very important random signal that plays a very important part in this communication systems. It is basically your noise signal. In fact, you have an entire course dedicated to your noise signal, the random process and noise systems. It has a huge importance in communication systems. But this is yet another classification. Deterministic, you can determine the value because it has a full-fledged mathematical model. And the random signals, which are not defined, you use probability as statistical concepts to define these, but they are not certain. They can behave in any uncertain manner. Yet another classification. So we'll stop here. We'll go for further classification in the upcoming videos.